Welcome to Ask and Learn.
So now we have, this is another actually kind of a difficult problem that for the third problem in the section, but we'll go through it, and it's mostly just getting the geometry correct. And in fact, when you're using energy methods, it's usually about getting the geometry correct. And in fact, a lot of problems is once you get the geometry correct, you can things then fall out. But it's the geometry that needs to get is often difficult. So we have this wheel or this semicircle, and it's rolling. I think you can probably picture it a little better in the figure. It's rolling on a surface, and it's rolling without slipping. And let's see here. So we're gonna say, this we have some angle theta that it rolls to, and so what we can do is we need to figure out the position of the center of mass. So the center of mass is, down some distance r bar from this point A, the center of the full circle. And that, if we're going to use the coordinate system where this thing was initially, so let's say before it rolled, it was right, the point of contact is right here. So let's use that as our origin. And we can figure out that y, so the distance from here up to here and then down to here, is r minus r bar cosine theta. So up and then down r bar cosine theta. And that gives us the y coordinate of the center of mass. Now the x coordinate, we have to say that it is, I drew this for a negative value of theta, so it's a little confusing, but x, we know we can figure out the x relative to the point here. We can figure out x very easily, and that is minus r bar sine theta. Right. So again, I've drawn theta to be in a negative value here, so that's a little confusing. Yeah, let me just leave it as that. But so that's relative to here, but we also know our origin was over here, and this distance here is how far it's rolled, and along a path here, and that is r theta. So that's the distance that it's traveled along this surface here. So the point of contact has moved over that much. So these are our position of our center of mass. Now, we can take time derivatives of those to get the velocity of the center of mass. For a semicircle, we know we can look up that r bar is, the distance from here to here is 4r divided by 3 pi, and in this case it's 0.212 meters. That in there. Now, we can say, okay, what is the potential energy? Well, that's the weight times the distance y of the center of mass above our datum, which we'll take as this. And so we know that. We have ycm. And now we can use our approximation for cosine of theta. Let's see here. I actually missed the term here, but it won't matter. But MWR bar. Okay, so we use our approximation for cosine of theta. That cosine of theta is approximately 1 minus 1/2 theta squared, and we get this expression here. And then for our kinetic energy, we have to, let's see here, we have to take the kinetic energy of the rotation about the center of mass, and then the translational kinetic energy. So this is the rotational, this is the translational kinetic energy. We can figure out the mass moment of inertia about the center of mass here by using the parallel axis theorem, or kind of in reverse. So we know JA equals JCM plus mr bar squared. So JCM is JA minus mr bar squared. And let's see here, JA is 1/2 mr squared. So that we can get that value. So we have that, since we know this, and this. Then we can take this squared plus this squared, and then we'll look some simplification. We get 1/2 m theta dot squared times this term here. Now, notice again that this is this is a nonlinear term, and we could use our approximation of 1 minus 1/2 theta squared. But in that case, we already have a quadratic term here, right? So what we want is our potential energy to be quadratic in velocities. And so to get that, we can just replace cosine of theta in this expression with 1. Okay? So if we used 1 minus 1/2 theta squared, then we would get a term that looks like theta dot squared times theta squared. And that's more than quadratic in theta. So if both of these things are considered to be small, theta dot and theta, then this thing is very, very small. And much smaller than a term that looks just like theta dot squared. So we can just use our approximation of cosine of theta equals 1 here. So we can figure out that if we look through back here, our equivalent stiffness is the term, the constant between the 1/2 and the theta squared. So that's W times R bar. Our equivalent mass is everything between, the coefficient here of 1/2. We have 1/2 MEQ theta dot squared, and we can figure out what that MEQ is. And that turns out to be this expression here. Just because we can simplify this thing down and then substitute in, and we get in the end it winds up being 3/4 mr squared minus 4 mr r bar. Now this is m over g, so we plug in our expression for the natural frequency, and so we get 2g r bar all over 3r squared minus 4r r bar. Okay? Plugging in values for that. Let's see here. Is that right? Let's see here. Something is looking a little strange to me in this problem. Let me go back and check my solution here. Back. Too far back. Alright, let's see here where there it is. Yeah, I think I wrote this wrong here, because if we take and multiply this through by 4, let's see here. How did I get this 2? I think somehow I let's just leave it like it without trying to simplify things. So the m's cancel out, and so we get, in the denominator we get this term without the m's, okay, and then in the numerator we just get g because of the weight and r bar. Okay, I guess I'm not sure why I had it. Anyway, this is the expression that we get, and we can plug in our values now since we are given all these things. Well, we look this one out, and we get 6.48 radians per second, and that gives us a natural period of 0.97 seconds.